Excellent. Okay, so now I am super excited to announce our keynote speaker. Dr. Angela Schoellig is an Alexander von Humboldt Professor for Robotics and Artificial Intelligence at the Technical University of Munich. She is also an associate professor at the University of Toronto Institute for Aerospace Studies and a faculty member of the Vector Institute in Toronto. Angela conducts research at the intersection of robotics, controls, and machine learning. Her goal is to enhance the performance, safety, and autonomy of robots by enabling them to learn from past experiments and from each other. That was actually only a small part of Angela's bio, and I'm super excited to now introduce her for our keynote speech. Welcome.
Can you hear me and see my slides?
Yes. We sure can. Welcome. We can hear you. You sound great, and we can also see your slides. So thanks for joining us.
Okay, great. Let me also start it here. Okay, welcome everybody. I heard some of the introductory words and I'm so sad to not meet the people in the audience. And I heard Josh say I would have also been able to see robots, which would have been lovely, but unfortunately I couldn't take the plane because I was sick and I think I'm still recovering a little bit. But I'm very glad to be here today and to talk about, can we build better robots through machine learning? And maybe we should also put there a question mark. I mean, can we? Because if we look at today's most successful robots, they do not rely on machine learning. Most of the robots are still in an industrial setting, in industrial manufacturing, in warehouses. Here we see also a Canadian example with Auto Motors. Some of them made it into our homes as vacuum cleaners or as flying cameras. But none of these examples really rely on machine learning. And neither do much more advanced tools such as the Da Vinci robot. So where is machine learning? In research, we've seen that machine learning really can provide advanced robot skill levels through, to complicated robots, such as walking robots, where they learn from experience and in simulation how to navigate very challenging terrain. There has been this example from OpenAI, where a robot hand solves a Rubik's Cube, something that I wouldn't know how to do without machine learning. There are other companies such as that do bin picking, and machine learning has a big impact in this field. And we have seen other amazing bimanual skills, such as opening a lid or putting objects in narrow spaces. But so far, those techniques still require massive compute and data, often rely on high fidelity simulations that are not easy to come by, and transferability of the skills is still a challenge. So they can maybe demonstrate this in the lab, but can they demonstrate it in the real world, in real applications and as a product? And typically, these approaches also have no guarantees of safety and performance. So maybe we'll take a step back and think about what is actually easy and what is difficult in robotics. And here I have this two-axis grid where on the y-axis I describe the complexity of the service. So how difficult is the task that a robot should do? And that ranges from a very simple, repetitive motion, like an industrial arm, to complex interactions with the environment. And on the x-axis is the environment they operate in. Is it very structured and known, or unstructured, and there are lots of dynamic objects? And so the majority of the robots in the first slide I showed you fall in this bottom left corner. They can do partially amazing skills. I mean, here you see the Boston Dynamics robot doing a flip, right? But this still is a single task in a very well-known environment. And so these tasks are generally easy, and usually they are solved by control theory in a model-based fashion because we know everything about the task and the environment ahead of time. However, if we aim to move robots out of those application areas that we saw initially, where they have made very important strides, we want to move to the top right here. So unstructured environments such as our homes or hospital or roads, and very complex tasks and interactions with the environment, interactions with humans, and high-level instructions where they have to decompose the task into multiple steps. And if we want to go this path, a model-based approach where we rely purely on our a priori. I'm so sorry, I don't know where I cut out, and I hope it was not on my end, but maybe it was. I'll share again.
Yeah.
Was it where I dropped out?
Yeah, this looks like the slide where you dropped out. If you want to just pick it back up, we're good to go. Thank you.
Okay, sorry about this. So yeah, we want to go to the top right, where robots have to deal with increasing uncertainty as they get closer to us, because they operate in our human-centered environments, in our environments such as hospitals, homes, and on our roads, where safety is, an absolute requirement. So I started my journey at the bottom left as, and I want to briefly highlight how we have solved problems in the past and how we can expand from there. So I started in control theory, and control theory means understanding dynamic systems, so systems that change over time, and then controlling them such that the closed loop behavior is the one we intend to have, right? And so this controller is designed based on a mathematical model that we have of the system. And some of you may have seen this in courses. And then we want to achieve behaviors with robots using control theory. And so in my PhD, I worked a lot with flying robots, and I want to show you one example from that time. In this example, robots moved along with music, and I hope you saw that and heard some of the music. So over 2.5 years, we created 6 choreographies of an increasing number of drones, ranging from 1, and at the end we had 6 drones, as you saw in the video. How did we do this? We analyzed music ahead of time. We associated motions to it. So we did, as humans, we did the choreography, we did a design, we used motion primitives such as circles and periodic motions, and those would be fed into a small trajectory adaptation module. You could call it learner, but it's a very minimal parameter adaptation, and then they would be executed by a controller, and we would estimate the position. So it was a hand-programmed choreography, you could think of each choreography to be one single task in an open, empty space where the vehicles, were very predictable. Nevertheless, this actually led to a performance on Broadway where a similar choreography was running in a Broadway show for over a year. And so this was probably the first flying vehicles on Broadway. So in total, it was 366 shows. And still, this is all pre-programmed, right? And the actor, acting well. But this is what what a standard robot program task looks like, right? We want a robot to achieve a task, and we program it by hand and design a controller that achieves the task. And then during my time at the end of my PhD, and ever since then, I've been interested to go beyond the limits of our prior knowledge and see how much robots can learn on their own. And so we have been doing this in Toronto and now in Munich for a while. And I want to show you a few of the approaches that we did in this direction. The key part being, how do we deal with this increasing uncertainty while also having an increasing demand for safety? So the question I really want to answer is, what are the first steps that we can do to achieve safe and high-performance robot control despite uncertainties? And so now I dive a bit more into the math, and later I come back to a few more high-level thoughts. So robots' behavior in the real world is always in some way uncertain. There's noise, there's friction that changes, there is, with the more and more of the use of the robot, the behavior changes. And one way to model this is by saying, I have a very good a priori model of the system from physics, but there may be unknown components and there may be random noise. So something that has a zero mean. And the same for our measurements. I may have a measurement model, but I also may have some noise. So this is the type of uncertainties we consider right now. It's still very agent-focused in a sense. And the second question is, what do we mean by safety, right? I think also that is a question to answer. And there are three things that we mean by safety. State constraints, meaning that the robot stays in its limited space boundaries. This can mean for flying vehicles in the room boundaries. For a self-driving car, this means staying on the lane. And for other systems, it may mean stay away from certain objects. So these are state constraints. Input constraints are the typical actuation limits that we have. And if we don't take them into account, we just have a wrong assumption about how the robot behaves. And the third one is stability guarantees. So for flying, this is very obvious. If we are not stable, that means the vehicle falls out of the sky. For self-driving car, if we have a non-stable controller, it could drive off the lane, like completely drive off. And so when we talk about safety in a learning setting, there are three main ways to consider it. One is we say we want to have minimal safety violations. So we want to minimize it, but violations can happen. And that's a valid approach and sometimes totally fair. For example, if the robot, is made out of rubber, it can drive into the wall and nothing happens, right? So it's kind of desirable to not crash, but it wouldn't be a big problem. Usually we have higher safety requirements, and the next step and safety level is probabilistic safety level. So with high probability, we don't want to violate the constraints. We don't want to hit the boundaries. And the last one is hard constraints. So 100% guarantee. And so in the mathematical formulation, that can look like this. So we limit the state and we limit the input. And we want also stability, of course. And a typical approach to this problem is we model the system. We do possibly some system identification where we gather some data from the system and to identify some parameters. And then we do the controller design. And that works really well in these controlled environments, such as in an industrial setting. The really nice thing about this approach is that we can actually test how robust we are towards errors. So even if we identified our model parameter slightly incorrectly, would we still, stay stable and not hit the wall boundaries? We can even explicitly take those safety constraints into account if we follow more of a model predictive control fashion. If we had known that the mass of the robot is between certain boundaries, and we know a lower and upper bound, we can also take this into account and design a controller that works for the whole range of parameter settings. And that is called robust control. And so, but it's important that usually every normal controller you design, even LQR, has certain robustness guarantees, so can handle a certain amount of parameter uncertainty. And I show you a few examples just to show, this can work. Works really well. Here, we try to introduce different disturbances. Kick the bucket, and the robot can control this. Right? We don't need any learning for this. Here we have this is a very recent work. Here we do a full body motion of the base and the arm, and where the base already moves to the next kind of person, while the arm still hands over the ball. So again, here there is model uncertainties, etc., different friction coefficients, and still this works well. We can even do this in a multi-agent setting, where here on the very right is our proposed approach of coordinating multiple flying vehicles in a tight space with obstacles where we have various aerodynamic disturbances. And we propose a very efficient way to do this. But even so, we have these obstacles in the way and multiple aerial vehicles that all have downwash and disturb each other. We can do this task. And finally, maybe the best example of all of this is where we actually approach the problem as a robust control problem. So here we want to balance objects on a plate. And if we don't take into account that there could be objects on the plate, they fall down. Right? But then we could make a conservative estimate about the objects on the plate. That there's something, that they have a certain mass and certain inertia. And if we do that, then we don't need to know exactly what is on the plate. We don't need the exact properties. But with a robust control approach, we can balance the objects. And I hope you can see those videos. So a model-based approach has a lot of advantages, and in a robust setting can even account for various variations in the system, even the object you balance and transport. So this is if we go at this problem from a completely model-based approach. The other main previous direction that people have been doing is completely learning things from data only. And this is usually, from the reinforcement learning community, where they don't assume they know a model. Sometimes, a model is very difficult to get. And instead, they work with data samples only. They only take data samples to then optimize a controller. And so the approach is the following. So the learner is what is the controller. So it just tries actions, sends commands to the robot, and observes what happens. And initially, these are random commands. And over time, it learns what actions actually get the task done. It's also a very task-specific approach, right? Because it evaluates the actions against a reward, against a particular task that needs to be done. But it collects relevant data for this task. And it tries usually to optimize the performance in terms of expectations, so the best expected performance over the long run. So that's how it deals with uncertainty, try to maximize the expectation of the performance. It's still usually in a quite controlled environment. But there have been amazing progress based on reinforcement learning if models are really hard to come by, which in robotics is very quickly the case if you have interactions. However, many of the early successes, they are still in lab settings or in simulation environments that have very little noise. One more recent example that was quite impressive is where a real hand solves a Rubik's Cube. This is a difficult task on its own, and then with a real physical hand. The thing is, what you don't see is that this only works 1 out of 5 times if we have a hard combination. So only 1 out of 5 times this reinforcement learning algorithm actually achieves the task. Otherwise, it either gets stuck or the cube falls down. So, if it would be a safety critical application, that would be absolutely not enough, right? Doing it 1 out of 5 times correctly. And so to put all this work into context is we recently did a review paper that tried to summarize this. And so here now you see the safety levels that I described earlier on the y-axis, and on the x-axis you see how much we know about the system. So that is similar to my earlier diagram. So from known dynamics to completely unknown. And so the traditional approach is really kind of sit in the left corner again. So at the top right, that's where we want to go, expressive kind of models, strong safety guarantees for unknown or complex systems in general. So safety guarantees and flexibility is really what we want. And the standard control approaches that I showed you lie here on the left side. So we have known dynamics. Sometimes this maybe have possibly bounded uncertainties that we know ahead of time, such as in the balancing problem that I showed. But then we often can give hard constraint satisfaction guarantees or probabilistic constraint satisfaction guarantees. So we really can provide strong guarantees. The typical RL falls here at the bottom. No, it makes no assumptions. It takes no model into account. It learns from data that is collected from interacting with the environment, but there are also no guarantees that this will work. Right, or converge. Like you're lucky if it converges. And so now people from both communities actually try to fill this wide gap here. And there are different approaches. And today I want to show you just a few from my group to give you an idea of what we can do. And that is not hopeless. So reinforcement learning researchers have often tried to encourage safety and robustness through the reward, through the task description, but it can only get you to soft constraint satisfaction. And then there have been approaches from the control theory to safely learn the uncertain dynamics, so safely explore what the robot doesn't know about its behavior or its environment. The other approach I won't touch on today, but it's also very interesting, is to certify safety after the fact. So you have something that controls the robot, and you minimally modify that control input to make the overall system safe. So I today mostly will talk about this blue area. And so I want to emphasize that a lot we do here is a feedback architecture design, and that's often where you can do a lot of clever things. And one example is a setup like this. That's probably the simplest example possible. You have a normal feedback controller, as I showed you before, and usually the signal you send in is what you want the robot to actually do at the output, right? So the signal you send in is R, I call it R here, and it's the blue line. But the signal that we see at the output is actually the colored lines. So every time the robot needs to do the task, it does it, but slightly incorrectly, right? We have basically a repetitive error that's always the same. So it seems obvious that you can do something to correct it. And so on the left, I just show a bit of math for those interested, but really, you can also focus just on the right side of the images. So really what we want is that what we send in is also what comes out. And so we see there's a constant offset, and we can iteratively just modify the input trajectory in a way that achieves the desired result and compensates for this systematic unknown error. And we can even do a bit more here to do this very efficiently. In reinforcement learning, we often talk about hundreds of thousands of trials. Here we do this in 3 or 4 because we use our simple model that we have of the system that we also use for the baseline controller to guide us in the right direction for the corrections. So, it tells us if we are too far left, what to change, in which direction to change our input. And then we can guarantee that we stay stable because it's really just a feed-forward type of approach. And so we did this for slalom, flying there without learning. There are just too many uncertainties that were not considered. And but we can learn the residual model error in a few iterations. I hope you can see it, otherwise I can send you links to the videos later. So we basically just have to learn the systematic model error, and since we correct immediately in the right direction, thanks to our simple model, we can do this very quickly. We can even learn things like a triple flip. So where the drone should do 3 times 360 degrees of rotation and come back where it started. So here for this for this approach, we learn a single task through repetition. So this can be expensive over time, right? I want the robot to do many different tasks. So we expanded this, and actually instead of learning just a feed-forward term, we learn an inverse model. So now basically the green should be the inverse of the gray box, such that the desired output matches exactly the actual output. And again, our model understanding can really help us. So for this inverse model, we use the deep neural network, but you could use any other nonlinear approximation. But the model understanding and understanding how robots move helped us to choose the inputs we need to put in here, so the red arrow, and made it extremely efficient this way. And again, we can also, by constraining some of the properties of the green box, we can guarantee that this is stable. And so we now wanted to show that we can learn arbitrary trajectories, and we showed it by following hand-drawn trajectories. So if you first learn the green box from periodic motions of different frequency, and then we show that we can follow arbitrary trajectories better than without the green box. And so what we can see is that on average, we have a 62% error reduction on these hand-drawn trajectories. And here's just a few examples. So here, red is what was drawn, gray is without the learner, and green is what you do with the learning module. So while this was still a bit of an academic example to show this, we also used it here when we want to show how precisely we can move a mobile manipulator to catch balls, where it needs to be very precise in time and space. And so here we use the same to add on to the existing tracking controllers of the base and the arm. So that's the nice thing about this approach as well. You can tag it onto any approach. You don't need to know the underlying controllers. You don't need to modify them if you don't have access. You just add it on top, and you can generally always improve the performance of the system. You see, we are not perfect. Here we have a prediction error of the ball, and here we are not tracking very well. So finally, one thing in this direction of an architecture is, what about if things change? So if the system over time changes, or I learn something on one flying robot, and now I want to use it on a slightly different one. So again, you can play with the feedback architecture and the feedback rates as well. And so the thing that now changed from the picture before is that we replaced the normal controller with a very fast adaptive controller. So very quickly adapting to changes through feedback. So basically a quick self-tuning controller. And so by doing this, and again, choosing approaches where we have guarantees for the red box. So there's, for example, L1 adaptive control, as well as Lipschitz neural networks that we use. We can actually, again, prove stability and also that the tracking error converges. And so one approach we use is we put a neural network here, a small one that has a Lipschitz constraint. So it's a Lipschitz network. We also used L1 adaptive control. And so this can be used if the robot itself changes. If you want to use the same learn model, the green box, you don't want to throw it away. You want to use it for two different robots, slightly different robots. So you basically just make them look the same by using this adaptive block. Or you can use it even for going from simulation to the real world. So if you learn the green box in simulation, and now you want to go to the real world, as long as you had this fast adaptation block in the simulation as well as in the real world, this can work because the fast adaptation block always tries to make this dash box look the same, behave the same. So it would make the simulation behave the same as the real robot. So it can also be used to bridge the model reality gap if you learn in simulation and then go to the real world. And so to just show you what you can do with this is we learn similar to the slalom learning with this AR drone and different underlying controllers, the green being this adaptive controller. And then we switch to a different drone. And so basically, if you have a normal underlying controller, even a PID controller, the drone needs to relearn this task again. But with an adaptive scheme, we can directly transfer this knowledge. Sorry. So this shows that feedback architecture can really be very, very powerful in robotics, and I think it's something we often underestimate. But all the examples I showed you require the training phase, and to learn. I'm sorry. And the next thing I want to show you is how can robots be deployed from day one without prior learning and still perform well. So we have the same setup. Sorry. And now the block diagram looks slightly different. So now we rely on learning the uncertainty in the model as the robot operates, and still doing this in a safe manner. And so for this, we use a probabilistic model called a Gaussian process and couple it with robust control. So initially, we don't know anything about what these unknown dynamics are, and maybe it just lies in this blue envelope, right? And over time, we collect more data. And that blue envelope shrinks. And so we basically get better and better knowledge about the environment and the dynamics of the robot, and can couple this kind of uncertain system with a robust controller. And 1 second. Okay. And if we do though, what is different to a normal model predictive control is that basically we say with high probability, I want my state to satisfy the safety constraints. And so let's switch to a video to give me a quick break. So here on the left, you see there's high uncertainty when the robot drives slow and conservatively. And then on the right, the uncertainty goes down and the robot can drive faster and faster. So it's a bit like humans, what we humans do, right? The better we can predict our environment and our own behavior, the more confident we are in our skills, and maybe the faster we execute a certain task. So this idea we explored further. I think it's quite powerful. So we try to make it more computationally efficient and also increase the prediction horizon. We also made it a more generic approach to safe model-based reinforcement learning. And one thing I just briefly want to show is we can use it to automatically tune controllers in a safe manner. So often, I'm sure you have tuned your controllers yourself in experiment, but you can get help with this type of approaches. So what it can do here is we can guarantee stability and performance. We don't need a training phase, and we can consider state constraints. Of course, there are always limitations, and the limitations are the overall setup that I proposed to you in the beginning, right? We assume it's a disturbance that acts on the dynamics of the system directly. We make some smoothness assumptions, and certain hyperparameters of this Gaussian process may also not be easy to know ahead of time. But nevertheless, this is an approach that at least explicitly takes into account that there's uncertainties in the environment that over time you may be able to find out from your data and reduce your conservatism. The last thing I wanted to talk about is I mentioned that there's kind of two main communities that dealt with the control of robots in the broadest sense, one the reinforcement learning community and one the control community. And both of them are interested to work towards safe learning in robotics in the broadest sense. And so we did a broad review paper during the pandemic around this topic to see, because both communities kind of approaching each other, both recognizing that data and models are very important to make progress in robotics. And so I highly encourage you to look at this paper if you're interested. We also have then released, as a result, a benchmark suite where you can develop your control algorithms and compare them. In particular, it includes constraints and prior knowledge. So you can actually explicitly define your prior knowledge and see how valuable it can be. And finally, there's also a webpage, saferobotlearning.org, and you can sign up to the mailing list if you're interested. So just a very, very brief run through this benchmark suite. If some people have worked with the OpenAI GIM benchmarks, this may ring some bells. So the environment allows to develop and benchmark robot control. It's physics-based, so certain benchmarks in OpenAI GIM have no connection to robotics. So this is really physics-based. And we have even for the quadrotor now a sim-to-real transfer option. So if you do a lot in simulation, we can also we have a direct bridge to transferring on a crazy flight drone. And so here you can now really define prior knowledge and see, how much your knowledge about the environment helps you to do a task. You can define safety constraints, you can define different disturbance injections, and we have certain simple systems like a cart pole and a quadrotor, and tasks such as stabilization and tracking, but these are also things we expand on. But no matter if you do any work on the control side of things, no matter of model-based, model-free, or learning-based type control, I highly encourage you to have a look, because lots of the approaches that are standard have been implemented, and you can compare your approaches against those. So standard RL and control, but also some of the latest safe RL and safe learning control. And, we are just exploring this ourselves. We don't know yet where this will lead us, but it's the first way, or the first kind of software framework where we can actually explore how prior knowledge helps us or limits us And so here you see we learned a particular task, and you see how well we do on the y-axis. We want to reduce this as much as possible to 0. And here you see the training data needed. And for a model-based approach where the model parameters are overestimated by 150%, the curve looks like this. And then for standard completely model-free RL approaches, the curve look more like this. So I need lots more data to get started, to get something useful. And then sometimes it takes quite a long time to converge, as for the green curve. And so here you see, with the model, you can at least save magnitudes of data, possibly. I also want to quickly hint towards something else, completely, non-robotics. We looked at what actually the impact of releasing code with publications is recently. And I want to just share that with you as well, especially if you're at the beginning of your career. So we looked at the number of papers that actually come with code, because we saw really a lack in our field. And so you see at NeurIPS, the top machine learning conference is pretty good. I mean, and then this is also a logarithmic scale, right? So at ICRA and also in the controls community is much lower. But if we look at all 3 communities and we look on the impact of papers that had code, it's significantly higher. So it's the colored boxes. And the difference increases with the number of years since publication. So generally, of course, there are limits to our statistics, but generally, the impact counted as citations is much higher if you publish with code. So finally, I am a strong proposer to combine models and data to achieve the type of safety we need as we get robots closer into our human-centered world. And there are many open challenges that we discovered as we looked at the literature. So there's plenty of space to contribute. The nice thing is we could kind of show that one could always formulate the problems that people have looked at as an optimization problem, and that no matter what, there was always a prior knowledge and data that was mapped to find the best controller. Right? And I mean, the notion of prior knowledge seems like a strong assumption in robotics, but it's something that we see everywhere in machine learning. I mean, we only made really good progress in image understanding once we used convolutional neural networks, because the convolutions were a very, very good prior to do image understanding, right? So it's not something new. There are many open challenges that we also highlight in our review paper, and I encourage you to look at them or see how your problem falls into one of those. So looking at product classes of systems, looking at the state estimation problem, because right now, everything I showed you, we assumed we have a measurement of the state or even the state itself available, which is not the case if you think about self-driving cars with LiDARs or radar and cameras and IMU. Many of the approaches are also lack scalability to complex systems. And sometimes the assumptions we make to prove safety need to also be verified or checked during operation. One open challenge that I also find very interesting, and we have done some very preliminary work in this direction, that robots infer automatically what is safe. And I think we are close to being able to do this because they can semantically understand the environment and, for example, understand what each object is and how they safely interact with this object. So that's also really an interesting direction. So kind of to finish this, the take-home messages are machine learning will be and is essential to build more capable robots. Leveraging prior knowledge about the structure of the problem will help us design efficient and safe learning algorithms. I think there's no question about that. And I also want to always emphasize roboticists that we design the closed-loop behavior of a dynamic system, which is quite different than other type of machine learning problems. And kind of just to be for a fun last thing, what actually happened with these dancing drones, we recently took this on again and actually designed countless of choreographies, not only 6, in 3 months instead of 3 years, with up to 9 drones instead of just 6. And now it can be programmed by non-experts. So how can this be? And in short, we combine again some prior knowledge and using pre-processing, but now we let a large language model actually design waypoints that fit the music. And then we pass it through a safe planner, safe trajectory optimization to make sure we are collision-free. A large language model would not be able to do any of this. And we can also check in simulation, but then we can run it on the real system. And we can even reprompt and say things in natural language, such as fly faster or further apart. So I think this is just showing that we are living in exciting times. And so here are just some last examples. So this was purely designed by the large language model.
Now we show how Swarm GPT generalizes to larger swarm sizes with these 2 choreographies, 6 and 9 drones.
Of course, there can be much more being done, but it's still interesting to see that a non-expert now can do what I did during my PhD manually. And so just as a higher level comment, I think it's really exciting to combine the system dynamics and control theory, which we even did in this last demo, because it has lots of advantages and gives us understanding with AI and machine learning, which can be a great human interface, enable more complex tasks, and can also be a creative tool to ultimately build the next generation of robots that can interact with us in our human-centered world. Thank you.